don't think I got that in camera. I just comment that what we got here, this whole expression, is the same as what we get if we just plugged in the sine and the cosine for x and y and took the derivative with respect to t. And then you made some kind of connection with the differential, and it's good if you recognize the differential in here. If you just take out all the dt's, you have the expression for the differential, right? And then it's almost like you divide by dt, but it's not really division. It's application, essentially this whole idea here. Okay, so this idea is really the idea behind the chain rule. When you got a function of one variable, an f of g of x, if x changes, that changes the value of g of x. Well, the changing value of g of x makes f in turn change, right? And you multiply those changes. That's all the chain rule is saying. Okay? So whatever the change in x does to g of x is represented by like g prime of x times the change in x. Okay? But then you gotta, so you've got that change, but you multiply that by the change then that you get from evaluating f at g of x, f prime at g of x. So without writing that out, that's a little hard to maybe understand. But the idea is here, in this case, changes in t cause changes in x, right? T changes somewhat, x changes. Okay? And of course, that change, you know, that rate of change is dx dt, the rate at which t causes x to change. Okay? And then those changes in turn cause changes in f. Okay? So your change in t is magnified or contracted or whatever by this factor, and then f changes in response to that change. I could draw pictures, but that's an idea I kind of want you to wrestle with a little bit. And we'll draw a picture in a minute, but you have an analogous statement for y. You know, changes in t cause changes in y, which in turn cause changes in x. And we know from our basic picture not far enough here. That, you know, if this is the y direction, this is the x direction. Here's your change in y. Whatever your change in y is causes a change up here, right? And here's your change in x, okay, which causes a change up here, and that's the picture we looked at previously, okay? Now, if t is causing y to change, then the derivative of y with respect to t determines how big a change you have in your y coordinate, right? If dy dt is bigger for a change in t, you're going to get a bigger change here. If dy dt is smaller, you're going to get a smaller change, okay? So whatever's going on with the y function, whatever the y function is, determines how big this change is, which determines how big this change is going to be, okay? And similarly with x, whatever your function is, if it's a cosine t, well, that's going to cause some change, okay? If it's an arctangent of t, that's going to cause some change. It's going to be very different than the change that you get from a cosine. Okay? So it's going to determine this dimension of this picture. Okay? Now you understand why I started you out with parallel pipeheads. You should really begin to appreciate that little chunk of wood. Okay? Because, you know, how many times have we referred back to it? Almost every day in almost every context. Right?
Yeah.
And there's another one that you're just going to love. Okay?
Today?
Yeah, we're going to talk about it. And I'll talk about it a little bit right now so your neurons start working on it. okay? Actually, neural circuits. Neurons don't really work on anything, but the circuits do. I think, as much as I know about neurology, conceptually, I've got an idea, but details, forget it. Okay, so now you know that the actual slope here is going to differ from the actual slope here. Okay, why is that? That's because dy or df dy is changing from here to here, right? So I'll just make a little note, okay. Now which slopes? It would be these slopes, okay? And they differ according to saying it very vaguely, the x derivative of that slope. What I mean by that slope, I mean the slope that you get if you confine the thing to a plane parallel to the YZ plane, right? Because that's where the slope lives. Okay, this is a little different YZ plane than this. So there's going to be a little difference in these slopes. Now we're talking about a small region down here, small delta x and a small delta y, right? But even with a small delta x and delta y, typically there will be a change in the slope here that depends on the derivative with respect to x of that slope, right? Well, what is that slope? Theoretically, you could answer this. You want to give me a shot?
It's the partial with respect to y.
Yeah. Right?
I guess at whatever point that is.
Yeah, well, we're just trying to get a pretty deep conceptual idea of something that's really important, okay? And it all ties up at the end of the semester with Green's theorem and its implications, okay? So if you understand this, you've already got a really good insight into Green's theorem, even if you forget it between now and then, okay? But it's also going to have implications here because it has implications for the problem I asked you to do today. Hope you did it.
Which one was that?
The one where we'll get to it. Because if you didn't do it, you're not going to understand it as well, but you still understand it.
The maxima and minima problem?
Yeah. Yeah, it's related to maxima and minima, okay? Where you did the parallelepiped and calculated the actual slopes, all four of them.
I didn't calculate.
Pretty sure, maybe, I forget how I phrased it.
I just constructed the parallelepiped.
Yeah. Well, there's a question involved with that. It's okay, we'll get to it because I think you'll be able to answer it. Okay. Our two C's here, this C is a little missing, but I do know how to spell. Incidentally, I ran into a word I didn't know how to spell.
I do that all the time.
Badminton. You know there's an N in that word? Okay, I spelled it. It didn't look right. It kept not looking right no matter how I rearranged it. There's an N before the T. Badminton. Ridiculous. Looking at birthday presents for my 5-year-old grandson. Okay, anyhow, okay, total different idea here. Okay, now back to this. Well, I'm going to stop the video here and we're going to go back over this and then I'll give you the payoff because we're right up to it, okay?